Welcome to Tolomatic public webinar. We're excited to have you with us, and we've got a great presentation here to talk to you about actuators, linear actuators. So I've been in the business here a little over 7-8 years, and if you had asked me when I joined the business about linear actuators, I would have thought it was a pretty short conversation and not that much detail involved. I can truthfully say there's a lot more technology involved than I ever had an idea about, and we will illuminate that for you here in the next 45 minutes or so. And we've got a nice technical presentation put together with, I think, something for everybody in here. So look forward to that. This is an ongoing series. We started back in March as the pandemic sort of hit North America here. We've been doing webinars with our distribution sales force, but we've also started doing more frequent public webinars as well, as people are still working remotely, have a little bit different schedule to their days. And so hopefully you're able to not only join us now, but look for future webinars, and we'll give you a preview of what's coming in about the next 5 or 6 weeks here. So we also have a number of ToloTalks that are based out on our website. I'll cover that at the end as well. Those are available for your viewing pleasure at any time. They're sort of 30-minute, typically plus or minus 10 minutes. Educational seminars, both on technology, on product families, and on applications. So with that, we'll get going here. Teresa, if you can scroll to the next slide. So we've got a staff here to present for you the actuator know-how. We've got a group of our applications engineers. These gentlemen are all based here in Minnesota, led by Teresa, the Zaske bunch. My name is Andy Zaske. I'm the VP, Director of Sales and Marketing here at Tolomatic, and we're excited to have you with us. Everyone's going to take a little bit of a 5-minute spiel to talk you through a different aspect of linear actuation. So we can scroll to the next page. What we have is a resource that we developed over the last few years. It's called an e-book, and this is a free resource that is downloadable from our website. Think about this coming out of your library. You pick it up off your shelf, and what we're going to do for you today is give you the Cliff Notes version of about 6 of the chapters inside of this e-book. We hope that that's interesting to you, and then we want to make sure you highlight with you that this is available to you not only today but every day as a resource around linear actuation. So feel free to pull it off the shelf at any time and or reach out and connect with us, and we'd be happy to walk you through various chapters and or technical details about the linear actuators. Go to the next page. This is a quick table of contents for that ebook. So about 15 different chapters, and the ones that are highlighted in blue are the ones that we're going to take you through over the next 30 to 40 minutes. So you can kind of read through that. The other areas are no less important, but we just didn't want to take an hour and a half for a webinar. So we felt that you maybe would prefer sort of a Cliff Notes version here and an introduction, and then can add and dig into the resource here on your own. So this is what we're going to go through. We're going to crack open the book, as it were, and we're going to jump forward to chapter 4 to kick things off. So go to the next slide, Teresa, and I'll introduce Kenny Green. Kenny's been with us for a few years now, hailing from Colorado. And Kenny, take us through selecting the right actuator.
Thank you, Andy. So part of the process of selecting the right actuator, and one of the first steps you'll want to look at, is choosing between a rod style and a rodless actuator style. The main difference between these two are kind of visualized in the pictures you see on the left. Whereas with the rod style, it is a rod that comes out of the unit and goes in and out, kind of like a hydraulic cylinder. And with the rodless, it's a slide that slides along a piece of extrusion, and it's kind of similar to a pneumatic slide. Some of the advantages with a rod style is that you get higher forces. They're designed specifically for pushing, pulling, or pressing applications, and you can get a higher ingress rating on them typically than you can with the rodless style. With the rodless actuators, you get guides and supports, so you don't need to have external guides for your loads. They are space saving, so because the screw or belt is inside the unit, you don't have to have a rod that comes in and out. It's a smaller, compact design. And with the belt design on them, which we'll talk about a little bit later, you can achieve higher travel speeds. So instead of being limited to about 20 inches a second, you can go up to the 100 inches, 150 inch second range. So we'll kind of go over some key design differences. Pictured on the right are the 3 different styles. So the first top picture, that's a standard rod style actuator design. What it does is it has a single bearing support for the screw, and that's on the back side. There is a bushing on the front that uses to help guide the thrust rod, and the nut is directly coupled to the thrust rod of the unit. The thrust rod, like I said, extends and retracts. This allows for a high force application because that thrust rod is directly in line with the screw and nut, so you're able to put a lot of force on there. And you can have the motor mounted, and this picture it's mounted reverse parallel where you can have a belt drive to it, but you can also have the motor mounted directly behind it. One thing about this design is it limits the stroke length you can use in the actuators. So our largest actuators go up to 64 inches of stroke. And when you get out to that stroke length, your pushing forces are limited because what happens is because the screw is not supported on the other side, you can get buckling load problems, and you are limited by the physical strength of the screw at the longer lengths. With the rodless design, there are 2 different types. There are the screw drives and the belt drive. So the middle picture is one of our belt drive driven actuators, and the bottom picture is a screw drive. The main thing you'll notice on those is the shaft where it comes out for mounting to the motor. With the belt drive, it comes out to the side of the actuator unit. And with the screw drive, it comes out directly in line with the actuator unit. Each design can be used in different applications. Both of them have internal guides, so that handles all the side loading and moment loading that you'll have with your load or forces. The carrier is connected directly to the belt or nut, depending on the design. What each of these designs allow for is a longer length and faster travel typically. For the screw design, you're typically using those for a higher load, higher force application because you can get more force out of a screw than you can out of a belt. But you do limit yourself on stroke length and speed because there's a physical limit to the speed you can turn that screw at longer lengths. And you start getting into supporting issues with that at longer lengths. Whereas with the belt design, you can get higher speeds. You do get a lower force because your force is limited by the belt, but that also allows for a longer stroke because your belt you can get a much longer belt than you can a screw. So at those, you can be looking at stroke lengths of up to 200 inches and speeds of over 100 inches a second. So lastly, we'll go over some application examples. Here's a list of several different ones that are just examples of this. But for rod style, classic examples are hydraulic replacement, so a hydraulic cylinder. These can be used in motion simulators, or a lot of times I see as pressing applications. With the rodless, common examples of those are pneumatic slide replacements, where you're replacing a pneumatic slide system, or gantry systems. Particular one is pictured on the right, and this encompasses 3 of our rodless style actuators on the X and Y axes, and then one of our rod style RSA actuators in the Z axes. So this is a common thing and allows you to be able to operate gantry systems effectively and without having to put in external guides for them.
All right, great. Thank you, Kenny. Now we'll go into chapter 5 in our ebook here, which is 10 tips for specifying electric rod style actuators. And Jeff Brandt, our application engineer, been with us about a year, coming from a combination of California and Minnesota. So turn over to you, Jeff.
Thank you, Andy. And yeah, I guess this section of the book, we like to call these 10 tips for specifying your actuator. I think, these are more so, you can look at this as more of a checklist to make sure you're kind of covering everything you might need. when you're starting to size your actuator, and for the interest of time today, and also to kind of help you remember this, I like to separate these 10 tips into 3 smaller categories. So the first one, calculations, and then maybe take your actuator out on a date, get to know what it's capable of, you know get to know a little bit of the background and see if it'll be a good match for you and your system. And then lastly, take a look at some of the environmental aspects. Especially right now, there's everybody likes to save the environment, and I think the environment is kind of on the top of our minds, and it should be also for you when you are selecting your actuator. So we'll take a closer look here at the math portion of this. This should detail tips 1 through 4 here. I think most importantly, out of this section, I would really emphasize calculating for electric and not another form of power, so not any hydraulic or pneumatic. The reason for this is that it's typically it's a little easier to oversize a hydraulic system or a pneumatic system. It's as simple as getting, putting a larger bore in your cylinder. The problem with that, if we try to oversize an electric, the capital cost starts to increase pretty rapidly. And so what we like to do is we like to make sure that we are getting you the best actuator for your needs, and you're not paying too much. That's kind of, again, the key point for the math section. If we go down to getting to know your actuator's capability, big one here I like to hit on is factoring in the duty cycle. So this is something where you want to make sure your application is fitting what that actuator is designed for. So whether you have a lane diverter on a conveyor belt, or if you're a kickoff on the conveyor belt system, and you're running 2 times a minute or even 4 times a minute, that's going to be very, very different. That might be more of towards the 100% duty cycle range. That'll be different than perhaps raising and lowering a table for testing, where you might do that once or twice a day. Now, all of our actuators are designed to be 100% duty cycle, but that doesn't mean, they won't work in that 25% duty cycle range. It just might mean, again, kind of reverting back to the first section there, we want to make sure that we're not giving you more than you need. And lastly, for that last chunk there on the environmental considerations, the biggest one, again, is also on the top here. That's going to be the operating conditions. Whether there is a larger amount of dust particles in the air, sawdust, or if there's water, any water spray, anything like that, that's really going to affect which actuator would be the right fit for you. We have certain actuators that are designed for those environments, and if you have a bit of a harsher environment and you're not quite sure where to go, feel free to reach out to us. We'd be happy to guide you in that correct direction there to make sure that you're going to get an actuator that fits your needs. And you might start to think, okay, holy smokes, this is a lot for me to keep track of as I'm starting to size my actuator. Conveniently enough for you, on our website, we have 2, we like to call them worksheets, one for the rod style and one for the rodless style that Kenny was referring to. These are a great way to keep all of the relevant application information in one area. And especially if you're working with any one of us applications engineers, we love to have this sheet filled out by you. This really helps us make sure that, again, you are accounting for all of this. You're trying to take in all of this information as well. And that really helps us work well with you. And also, I think some of the guys later on in this presentation today will kind of elaborate on different sections of this sheet relate to that. But those are available for you to download from the website. And lastly, if you are curious, about some of those other top 10 tips that I didn't really hit on today, go check out the top 10 tips ToloTalk that we have on the website. That was a ToloTalk that I did along with Nate Anderson, who you will hear later on. Otherwise, feel free to call the apps team. We would love to walk you through anything you might need, to, you know, any more information you have about your application.
Thank you very much, Jeff. Say, just a quick reminder, if you do have some questions or comments or suggestions, I would welcome that. Please feel free to click on the chat button and you can type those out. And if we have some time at the end, we will walk through and address those, or if there are comments and suggestions, we'll collect those at the end. So appreciate that from everyone. Thanks, Jeff, for that. And then we'll move over. Chapter 6 is selecting right actuator with belt drive or screw drive. So I'll leave that out there as a tantalizing chapter you can check out on your own. And then we're going to skip over to chapter 7, which is on screw selection. And Michael Witchen's been with us about 3 years as an application engineer. And Michael, I'll turn it over to you.
Thanks, Andy. Yeah, and as Jeff had mentioned, yeah, there are plenty of variables that you want to make sure you consider when you're sizing up an electric actuator. And one of the major elements that you want to consider, especially is with the screw drive, is what screw you're going to use. So, I mean, with these screw drives, there are plenty of different options that are available. You've got your solid Acme screws, you know, the Delrin nuts, the ball nuts, roller screws, bronze nuts, and they all kind of have their own features or their kind of specific situations that they fit in best. You know, ball nuts are going to be extremely efficient, allow you to go really quite fast, while a roller screw is going to offer you, you know, an extended life. And sometimes if you aren't able to use a brake in an application, a bronze nut is going to be your best option because it's got that ability to prevent back driving. So all of these are different kind of aspects that you want to take into account when you're sizing up your unit. And they've all definitely got their force ranges and speeds that they can hit as well. So we're going to go into a little bit more depth on that. So two of the main screws that we'll see when we're sizing up a unit are the ball screws and the roller screws. And that's because they're going to offer you the highest force range that you're going to see. And as you can see here, there's kind of a nice diagram on either side. The ball screws are actually what's going on there is we've got, you know, ball bearings rolling around inside that nut. And basically the load is going to be shared across all of those different bearings, you know, on those 2 points. Now, that's going to be a very low friction screw option. And that's going to allow you to get quite a bit of speed out of there. And then it's not going to generate too much heat. You're going to see a pretty good life estimate with those ball bearings. Now, roller screws are very similar in the fact that you've got a bunch of different rollers, but as you can see on the close-up on the right, you've got the threads that are lining up there. So there's a lot more surface area that's sharing that load. So this allows the force to be spread out more. It's going to give you a much higher life capability. That's going to be really great for pressing applications, kind of that repeated, you know, I'm hitting the same point with high force every time. And that, yeah, that gives you an increased life estimate, but we also need to be careful of, you know, the heat that's being generated there. And that's one thing that Jeff mentioned too, is that duty cycle piece. So, you know, knowing the worst case scenario for all of these applications is going to give us the best, most accurate life estimate we can provide too, and help us decide what screw is best for an application. Now we actually have a video here too that kind of shows the inner machinations of that roller screw. So we're gonna click on that and let you guys have kind of a close and personal viewing of that. These are available on our website as well.
You can find these videos on our Tolomatic YouTube channel as well. So, and then they have fun music that goes along with it, which doesn't translate as well in the Zoom meeting here. But
yeah, so yeah, I wasn't sure exactly how the sound was going to play through in there, but yeah, no, you definitely can dance along if you want to later on. But now here you'll also see we've got kind of one of our charts right from our catalogs, and this is going to go through some of the terminology that you see with these screws. And this is a lot of the information we need to take into account when we're determining what frame size actuator we're looking at, you know, what screw type. So, different screws obviously have different force capabilities, but that increases when you can go up to a larger actuator. You can fit a larger diameter screw in there. So just trying to kind of go through this chart, you're going to see obviously the RSA size itself. So that's the frame size of the actuator on the far left. And this is going to include, 64 all the way down to our 12 size RSA, the really small guys. Then you're going to see the maximum stroke, and that's going to be a limiting factor for, most applications when you are deciding whether you need a, rodless or a rod styles. If you need to go above and beyond that, oftentimes we're going to need to look at a separate technology. But if there are applications where you kind of button up against that limit, or you need to go a little bit further, by all means, give us a call. We can definitely look at what options we have available to make, extended options as well. The third one is going to be that screw code, and you'll see there's kind of a nice legend on the right-hand side, and that was something we touched on right away. But the BN or the SN or the BZ, those all are codes that basically just call out exactly what type of screw is in there. So we've got the ball nuts, we've got the roller nuts. Solid nuts are going to be those Delrin nut options and the bronze nut. And then the second part of that code is actually going to have to do with the lead or the turns per inch in there. So basically that's telling us how many revolutions of that screw we need to get 1 linear inch of travel on that actuator. So the SN04 is going to have a 1/4 inch lead, or else it's going to require 4 revolutions to get that full inch of travel. And that's going to be a big factor when you're looking at the speed of your application, because the tighter that lead is, typically you have to be more concerned about how fast you're going, because those screws have critical speeds that we need to be careful of before you run into issues, whether that's the screw wearing out faster than desired, or whether that's the screw actually whipping around in that actuator. So another aspect is going to be the accuracy and the backlash. That's going to be a big piece, especially in like pressing or repeated move applications where you're trying to hit exactly the same point. We can hit fairly tight tolerances on these, and we can even look at zero backlash options if they're needed in other applications. But typically you're going to see the highest accuracy is going to fall in that roller screw category. The next two are kind of ones that we want to make sure we touch on, because oftentimes they can get confused. So you've got your maximum thrust is going to be what the actuator itself with that screw is capable of. So that's going to be our limiting factor in terms of what loads or forces we can apply with that unit and screw combination. The dynamic load rating is actually a rating that's based on just the screw and nut itself, and that's used for calculating life. So when we're going through and trying to figure out what actuator size and screw is right for our application, we want to make sure we're always using that max thrust first. And if there are ever any questions about that, by all means, give us a call. We can help step through that process with you as well. But that's going to be the biggest, kind of screw terminology and kind of the differences between those screws. And if you guys ever run into problems with your application, by all means, feel free to reach out to us as well.
Thank you very much, Michael. Appreciate it. A lot to learn about screw technology. And then one of the questions that everyone has is, how much work can it do and how long is it going to last? So Nathan Anderson, application engineer, been with us about a year, is going to take you through some of the key things that we can calculate for you and give you a fair estimate on life expectancy as it relates to ball screws and roller screws. So Nathan.
Thanks, Andy. So when selecting an actuator, life is a very important consideration that you want to take into account. Oftentimes we can oversize actuators to provide longer lasting solutions. So there are multiple routes you can take in choosing an actuator for your application, not only just choosing what would be most cost effective. So we do have an ebook and a pamphlet on life, which has more information in it if you want to dig a little bit deeper. But we're not going to touch on everything in there in this presentation. So the 4 things we're going to kind of touch on would be the B10 to L10 estimates, load factors, variables to consider, and then PV limits for solid nuts and Acme screws. And it's important to note that your actuator, like a car or any other mechanical assembly, will last longer if you take care of it. So some of our actuators require regreasing, some don't, for example. And it's also important to note that these are estimates because we cannot predict the future, and they're not a guarantee of life. So, ways to estimate life. So our L10, B10 is a calculation of a life at which 10% of the bearings in the application can be expected to have failed due to classic failure fatigue. So 90% will still be operating at this travel distance. It's equal to the dynamic load rating, which Michael touched on, over the equivalent load. And if your load is constant, you can just put that number in here. If it varies over the stroke, then there's an equation that averages the loads given the proportion that they are represented in per the total stroke. That's in the pamphlet. As you can see, it's a cubic function. So small changes in the DLR or dynamic load rating of the screw can change the estimated life pretty significantly. And this is all multiplied by the lead. So that's it for ball and roller screws. For linear bearing systems seen on our rodless actuators, we have an L10 of 5 million linear meters of travel, given the load factor does not exceed 1, and noting that this varies on operating conditions, combined loads, etc. So it's important to look through the catalog of the actuator you're looking to use and the life estimates we can give for those actuators. So there are limitations on estimating life. We cannot compensate for all the variables that affect life of an actuator. If ingress of a corrosive chemical occurs, for example, that's going to limit life. If the grease liquefies and doesn't lubricate properly, that's going to also limit life. And I have also included a picture of our MXB series actuators below those variables because we do not provide belt estimates or lifetime estimates of our belts, which people normally have questions about. Due to the number of variables that affect belt life, we just can't accurately estimate how long they're going to last. And the fourth thing we're going to touch on are solid nuts Acme screws, and so the PV limits for those. This is another key screw technology we have at Tolomatic. The PV limit is a function of pressure and velocity, which is where the P and V come from. And it's a thermal consideration, as heat buildup is a function of these two variables. We cannot provide life estimates for these nuts due to uneven wear and inconsistent thermal impacts on the ball nuts, or the solid nuts. So this is just the only guidance we can provide on the life, which is sizing under the PV limit for the actuator. And that kind of sums it up for life. So if you want to dig deeper, you can look into the catalog that we have or the ebook, or contact another apps engineer at Tolomatic.
Great, thank you, Nathan. So a lot of technology there. We've gone through 4 chapters we're going to highlight. We've got 2 left. There's a lot involved here as we're skipping around, but there's a lot of knowledge we were able to share here, but also I think a teaser of other things that you can check out on your own, or as Nathan just pointed out, we welcome you to reach out. You can contact an engineer. We have an Ask an Engineer quick link on the front homepage of our website. We've also got an 800 number here. Feel free to give us a call, and we've always got people available during business hours that would love to talk to you about your application. We spent a lot of time talking about the actuators themselves, the rodless and rod style actuators, and Tolomatic has a broad portfolio of those. But we're going to spend the last 2 chapters talking about what drives those actuators. So we've talked about the belt and the screw and the transference of power from rotational to linear travel. And Enrique and Tim, Enrique first here is going to take you through what is attached to this actuator to create that motion. So Enrique.
Hello, everyone. Good morning, good afternoon, or evening for the people in other parts of the world. Thank you for joining us. Hopefully you're healthy. So yes, thank you, Andy. So in Tolomatic, we don't only sell actuators. We also have an offering of stepper or servo motors or gear heads. One of the main questions we get all the time is, which one do I choose? Do I choose a stepper or do I choose a servo? The answer is not definitive. Every one of them has its advantages or disadvantages depending on the application. The servo motors, the advantages they have is that you can control position and speed in a better way than with stepper motors. You have a better accuracy the reason behind this is that you have to use closed loop control for these motors. In the bottom left of the page, you will see an example of how a closed loop control would look like. So basically, I'm just going to give you this quick example so we understand what a closed loop control example is. So for example, if you're commanding a certain position, let's say that you want to move to 100 millimeters, then your PLC will send that command to or amplifier, or some people call it also a drive. So this commanded position will be the input of this amplifier, which is a pink triangle in that image. The drive will take that 100 millimeter number and send a command to the motor, so the motor performs that move. So the feedback from that motor is called an encoder. The encoder, what it'll do is measure if you got to the 100 millimeter position or not, and provide some feedback of that position to the original position, which is a minus sign on the circle on the left. So once that happens, the difference between the commanded position and what the encoder said it got to, it'll be the error. So this error is what the amplifier will be working with to try to adjust the motor to reach the commanded position at the end. So let's say that encoder measured 99 millimeters instead of 100, or error will be 1 millimeter, and the amplifier will try to correct this until it gets to the 100 millimeter position. Some of the disadvantages is that the servo motors are more complex and more expensive. When I say expensive, just as an example, for example, flat screen TVs, when they came out, they were pretty expensive, right? But now they're not. It's the same with this type of servo motor technology. Technology advances pretty rapidly, which allows prices to go down. So servo motors have come down in price quite a lot in the last couple of decades, but still, they're more expensive than stepper motors. It requires more tuning. Also, that's one of the disadvantages. For this amplifier to work correctly and to reach the commanded position, speed, acceleration, deceleration, etc., you have to tune the unit. You would do this through some software that allows you to adjust some gains like proportional, derivative, or integral gains, which would allow you to reach the commanded value in a better way. So it demands a little bit more tuning, but it's at the end, it's a better accuracy out of a servo motor. All right, now for the stepper motors, some of their advantages is that you don't need to have a closed loop control as you do in a servo motor, which means that you don't really need an encoder at all points, right? So that could reduce your cost a little bit because you can just command the position, and the stepper motor will do that with a number of counts that will rotate the shaft until a certain point, right? So that's one of their advantages. Another advantage is that they are lower in cost than servo motors, 30 to 40% less expensive. Also, you can develop a really high torque at low speeds, which is very important with for some people that have slow enough applications that could use a stepper motor. We're gonna go through that a little bit more in a couple slides here. High detent torque, the 10 torque, which means is that even if you are not rotating your shaft of the motor, it is harder to back drive it with a stepper motor. Some of the disadvantages is that you don't have, if you don't have enough torque, it can lead to lower accuracy. And by having less accuracy, you can generate higher costs, not only in your in the development of your software, but also in your actual process. Having less accuracy always could develop problems, which could lead to quality issues or dead times, et cetera, et cetera. So, and another thing could be that you could have some motor resonance when there's torque loss. So if you please click twice in this same slide, Teresa. You could click, yeah, one more time, please. There we go. So the way these stepper motors would work, you see the coils A and B. once these A and B coils are energized, the rotor of the stepper motor will locate itself in that position, right, that you see on the left side. But once you stop energizing those coils A and B, and now you energize C and D, then the rotor will do a transition magnetically to this next set of coils, which will generate this rotation little by little. This is normally called a step. So that's what they're called stepper motors, correct? So once you start changing the energization of the coils, then you will create this motion rotary in a rotary motion. So, all right, if you go to next slide, please. One of the main differences, as I was saying before, is how much speed you can reach with a servo or a stepper motor. With a servo motor, as you can see in this graph, please click once again, you can reach, in some cases, up to 6,000 RPMs, correct? The more RPMs you have, the least torque you will be able to develop in general cases. That's how motors work. In the case of the servo motors, they can go faster than a stepper. Another click, please. Now, as you can see, in the stepper motors, you can reach velocities up to 1,200 RPMs. So if your application doesn't need to go too fast, as you can see in the stepper motor graph, the torques are pretty considerable at low speeds. So if your application is going slow and you want to develop a certain amount of high torque, then a stepper motor is a great choice as well. And also it'll let you reduce your costs. Both in the selection of the motor, it will be 30 to 40% less expensive. And also you probably don't need an encoder to provide you with feedback, right? So you save money if your application is low enough. Next slide, please. So what determines, another click, please. What determines the speed of a motor? Typically, the voltage in our drives goes from 10 to 60 volts. And that voltage is the one that is used to reach different speeds. With 24 volts, you will be able to reach less speed than with 48 volts. It's the same case both in servo motors and stepper motors. We call this a higher voltage 48 VDC, but in reality it's not high for some motors that are out there in the marketplace. We offer motors that go up to 460 volts of VAC, which we don't have a drive for those, but we do offer motors with higher voltage. So, but for offering of our drives and motor systems, we offer up to 60 VDC. So again, just to conclude on this, the higher the voltage, the higher RPMs you can reach. Next slide, please. Another thing that people use to be able to generate more torque are gearboxes. What happens with these gearboxes is that you take the speed that you have in the motor and you connect that shaft of the motor directly in the back of these gearboxes, and that high rotational speed of the motor will translate of a slower rate in the output shaft of the gearhead, but with more torque. So you can have reductions such as 3 to 1, 5 to 1, 10 to 1, etc. And all those reductions mean that your motor will rotate 3 times faster, but at the output of the shaft of the gearbox, it'll generate 3 times more torque. So it's a balance between how much speed you can achieve with a motor against how much torque you need to develop. So there's some softwares out there that will calculate this for you, such as motion analyzers or such. But internally, we also have our sizing software that is available in our tolomatic.com website that will calculate this for you. So it's interesting. If you want to start playing with the sizing software, you're more welcome to. It's free to join. You just need to set up your new account and you can start plugging some numbers in terms of your application requirements. We offer as well gearboxes like these ones, but if we don't have it, we can get it for you as well in the ratios that you need, or we can design the actuator to accept either the gearbox you want or the motor you want from a third-party company. So that's it for me. Thank you for your time, and hopefully you stay healthy.
Hey, thank you, Enrique. And that's a great segue from servo stepper motors and gearboxes into the your motor here. So you have your motor and or gearbox. Now you have to mount it to your actuator. And Tim Nijelski has been with us, I won't say exactly how long, Tim, but a while. And this is our last chapter we'll highlight in our actuator know-how for machine design section here. So take it away, Tim.
Thanks, Andy. And good morning, everyone. Once we know the performance characteristics of the motor or the gearhead we need to mechanically mount that to an actuator. And ToloTalks some years ago has developed a program, mechanical motor mount program called Your Motor Here. Your Motor Here is found on the front page of our public website with the symbol here. Now, why would we use YMH? Let's answer that question first. Well, you'll definitely save lead time, you'll save money, and the mechanical implementation is much, much simpler than having to customize motor mounts for all the different manufacturers. Now here's some interesting information on how the program is set up here. We have over 70 manufacturers, and these are all the major manufacturers of servos and steppers. We've incorporated around 3,000 motor models into the database. This gives us a really high number of motor and actuator combinations. Basically, this program brings up a set of dimensions, which we'll look at in a minute here. If your motor model that you have or gearhead isn't in our database, there's two things that can happen. We can do a manual search internally, or we can actually make a custom motor mount if the dimensions just don't fall into the YMH dimensions that we need. How do we use this program? Let's take a look at how it's implemented here. Basically, there's 4 easy steps here. This is for an inline actuator here. This is the simplest. We select the actuator, which we already know. We select a manufacturer. Let's use Allen Bradley for an example. We select the manufacturers of the motor series. Let's use the popular MP series, which we do about every other day here. And then we select the actual motor model that we're going to use. This program will generate a 6-digit code. And this code here actually means an Allen Bradley MP series and a specific model, which is, I think, like a 115 millimeter frame. Once we have a code, then we can go to our next step here is we want to verify these program dimensions with your catalog dimensions. And it'll list all the pertinent dimensions, basically on dimensions you'd suspect, like shaft diameter and length, mounting bolt circle, and pilot diameter, which actually aligns the motor. And then once we have a verification that our dimensions are correct, our next step would be we want to put this motor mount on the actuator and then put that into our design. So we can go back to our website, to our CAD library, we can download a 2D or 3D, and then this can verify fitment of the entire actuator. And that's about all I have. Thanks.
Perfect, Tim. Thank you. So we try to make it easy here. The Your Motor Here program has been operating well for the last decade or more, and really a tremendous database and a value to our customers. So that concludes the 6 chapters of the ebook that we were going to highlight, but I just wanted to show you here there are more that you could check out. So everything in green are the things that we did not cover in today's webinar. So I encourage you to go out, grab, we have 2 digital resources that we highlight here. One is a resource on electric linear actuators. That's what we've been working our way through with the 15 chapters. And the other is what Nathan talked about, the actuator life, how to estimate your life for ball and roller screws. Here's a hyperlink at the bottom of the page that you can write down, or you can go to our website and search up both of these resources for you. Or if you want to send us a quick note, we'd be happy to take you through that as well. So we'll go to the next slide. We'll just wrap up with a few things. You can go to our front homepage of our website, and it's easy to click on the left-hand side. There's a purple-headed character there with a brain with gears in it moving around. Those are our engineers. So we encourage you to click on that link. You can contact an engineer, fill out some information, and our application engineering team will get back to you quickly. You can do this if you just want us to send you that ebook. That would be fine too. Or if you have particular technical questions on linear actuation and or Tolomatic products. So feel free to do that, or you can send an email to that help@tolomatic.com. I just want to highlight the webinar series. So you see on the upper left-hand corner here our homepage. So a couple things to note. The contact an engineer, like I said, on the far left-hand corner, the sort of blue head with the gears. The actuator sizing next to that is our online sizing tool and software. So a lot of the details and information you've learned today would be applicable there. Tim referenced the next two, the 3D CAD library we have of our catalog products and the Your Motor Here program. You click on that link and enter that data from those drop-down screens, and you can get that YMH code. We've got our Find a Distributor link here. So if you want to know who our distributors are in your area, you can click there. We've got our ToloTalk webinar series, and that's what the rest of this page is highlighting. So over the last 6 months, we've done over 40 seminars. These are about 30-minute videos. About 30 of those we put on our website. We've had over 10,000 people look and review those. There is a menu, sort of a table of contents at the top. You can see those quick links. And there's a broad array of things on technology, on our product families, and then a lot on application examples that are out there. So I encourage you to go check that out and see what might be applicable and of interest to you. Invest another 30 minutes in a educational opportunity that is waiting out there for you.